In this video, we'll discuss the SIR model of disease dynamics. This doesn't really have anything to do with the material we've been looking at recently. We won't use fixed point analysis to study it, but with the COVID-19 outbreak, it's undeniably timely. I hope you do not find this material anxiety producing, but please let me know if you do. We'll look at a limited class of disease with the SIR model. The disease is infectious, passed from person to person, and the disease grants immunity to it once you've had it. You can't get it twice. We'll also assume that the outbreak is of a relatively limited duration, so that we can assume the number of people in the population remains approximately constant. People can die from the disease, but we'll neglect unrelated deaths, and we'll neglect births, immigration, emigration, or other non-disease related changes in the population. We can classify people into one of three categories. People can be susceptible to the disease. That is, they could be able to catch it. They could be infected by the disease, and they could be removed from the situation, either by dying from the disease or recovering from the disease and no longer being susceptible. We'll call these categories S, I, and R. People can pass from S to I, and they can go from I to R. The number of people in these categories will be S of T, R of T, and I of T, because of our assumption that the population isn't changing, except perhaps due to the disease. We have that S of T plus R of T plus I of T equals N for some fixed N. How does S change with time? That is, what's ds dt? Well, to calculate the number of infections over a small time interval, remember that the only way to leave S is by being infected and going into I. We'll start with S I. This is the number of possible ways that a susceptible person and an infected person could interact. That's because such interactions are the only way the disease can spread. We'll multiply this by P, which will be the probability that a randomly selected, susceptible, uninfected person do interact over the time interval. And then we'll multiply that by W, the probability that such an interaction results in infection. Since these are both constant, we'll combine them together. This is the rate at which people are becoming infected, which is also the rate that people will leave the susceptible category. DI, DT. The rate at which the number of infected people would change. We've got this RSI term corresponding to people leaving S and entering I. But we've also got people leaving I by recovering or dying and entering R. The number of people who do this is proportional to the number of people currently sick. The more sick people there are, the more people there are to either recover or die. So we've got this negative gamma I term. And dr dt will be positive gamma I. Now, this is a system of three equations and three variables, but we can get away with only studying two of them. Notice that R, capital R, it doesn't appear in either of these two equations. We can understand S and I without understanding R. And because S plus I plus R is a constant n, if we can understand S and I, we've got a handle on R as well. In this video, we have introduced the SIR model. We will now proceed to analyze it, although we will not actually solve it.